Hello, everybody. My name is Kenji Shibata. I'm from Utsunomiya University, Japan. Today, I'm going to talk about open space-based motion prana of mobile robot for multiple obstacle avoidance. In recent years, mobile robots have been assisting human works. For example, transportation, training, guide, and so on. The robots needed to move autonomously in warehouses, train stations, and airports. These environments contain multiple obstacles such as desks, shelves, and people. In the presence of these multiple obstacles, the robot must move safely and efficiently in navigation. So the robot needs to avoid obstacles. Therefore, the purpose of this work is multiple obstacle avoidance by mobile robot. In previous work, motion planning for obstacle avoidance has been proposed through imitation learning. Motion planning is to determine the following outputs for sensor inputs: linear velocity and angular velocity. The input to the motion planner is perception images and depth images. This figure is the perception images, and the perception images were generated through object detection. With this approach, the robot successfully avoided an obstacle. However, it was difficult to plan the motions for multiple obstacles. This is because the robot was instructed to avoid a single obstacle. Therefore, the robot is required to plan avoidance motions for these obstacles. However, the motion instruction cost increases with the number of obstacles in a framework of imitation learning. For this challenge, we focus on the area which is not occupied by obstacles. The area which is not occupied by obstacle is called open space. The open space images is generated through image segmentation and object detection techniques. For image segmentation from RGB image, first off, we use UNet, which is one of the semantic segmentation methods. All the pixels of RGB image is classified into a road floor surface where the robot can move and others. Open space is colored by red and the other is colored by black. However, the area between the legs of the person is also recognized as the open space. Since the robot might move toward the floor between the legs, we additionally detect the person as the obstacle from the RGB image. For the person detected by yellow as the obstacle, the bounding box is drawn by green as shown in this figure. In segmentation image, the pixels inside the bounding box are filled in black. This generates an open space image. So here, let us explain the two motion planners. The first one is what we propose the motion planner 1 based on CNN with an LSTM. The open space image is fed as input to the motion planner. Through the convolution and pooling layer, features are extracted from the open space image. In the fully connected layer, an LSTM block is applied. Finally, the next linear and angular velocity are determined as the motion output. In the previous motion planner 2, perception images and the depth images is fed as the input to the motion planner based on CNN with LSTM. These two motion planners are applied to the robot. Next, autonomous navigation. This figure shows the occupancy grid map built by the robot beforehand. The robot moves toward Z while avoiding the obstacle. For motion instructions, the robot avoids to the right for obstacle in environment A. And the robot avoids to the left for the obstacle in environment B. Next, we explain setting for experiments. In the experiments, the proposed motion prana 1 and the previous motion prana 2 are used. In each of the environment A and B, the robot repeated the navigation trial 5 times in total. For comparison of the motion planners, therefore, we compare the number of succeeds in the trials from S toward Z. This is the navigation result. In environment A and B, the robot reached the destination in all the trials, regardless of the motion planners. The robot avoided to right for environment A and to the left of for obstacle in environment B. Next, we explain autonomous navigation environments with multiple obstacles. In environment C, a box is arranged as an obstacle in addition to the standing person. In environment D, 2 boxes are arranged as the first obstacles, and the person is standing as the second obstacles. In each of the environments C and D, the robot repeated the navigation trials 5 times in total. For comparison of the motion planners therefore, we compare the number of succeeds in the trial from S toward Z. Here, this is the navigation result for multiple obstacles. The robot based on the motion planner 1 with the open space image input successfully reached the destination while avoiding the obstacle all the trials. On the other hand, the robot based on the motion planner 2 with the perception and depth image input did not plan the avoidance motions and stopped by the obstacle ahead. Here, this figure shows the navigation trajectory in environment C, motion planner 1. We can see the robot moved through the 2 obstacles in all the trials. To discuss the navigation results, we show an open space image. And this is the RGB open space and feature map. In the RGB image, we can see the box and the standing person as the obstacles. These obstacles are on both sides in the image. Therefore, in the open space image, there is the open space between the obstacles, and features around the obstacles are extracted. As a result, the robot moved through the open space between the obstacles. And this is the navigation trajectory in environment D, motion planner 1. The navigation trajectories varied in each trial. In some cases, the robot avoided the box obstacle OD1 by moving both to the right and to the left. In order to examine the different avoidance motions, we compare 2 open space images. Even for the same obstacle, it appears in various positions depending on the position and the orientation of the robot. So we can see the open space in left side in this figure. As a result, the robot avoided the obstacle to the left. On the other hand, we can see the open space in right side in this figure. As a result, the robot avoided the obstacle to the right. In this way, different open space image inputs cause different avoidance motions. Okay, let us conclude this presentation. The purpose of this work is multiple obstacle avoidance by mobile robot. However, the motion instruction cost increases with the number of obstacles in a framework of imitation learning. For this challenge, we focus on open space. The robot, based on the motion planner, successfully avoided multiple obstacles. In future work, we will focus autonomous navigation in more dynamic environments with pedestrians. That's it. Thank you very much for your kind attention.